What if I told you the biggest battery deal in history wasn't for lithium, or some futuristic material discovered in a secret lab? It was for a battery made using an element that's sitting in almost every kitchen. No, this isn't clickbait. A single order for 60 gigawatt-hours of sodium-ion batteries has just become one of the biggest moments the energy industry has ever seen. To understand how massive that is, it's enough energy to charge every smartphone on Earth at the same time. That's billions of phones plugged in simultaneously. The company behind this record-breaking deal isn't a newcomer either. It's CATL, the world's largest battery manufacturer. And the secret ingredient behind this technology? Sodium, the same element found in ordinary table salt. Something so common that most people would never imagine it could challenge one of the world's most important technologies. But this breakthrough didn't happen overnight. It took nearly 30 years of research, billions of dollars in investment, and decades of failed experiments before scientists finally solved a problem that had blocked sodium batteries for over 40 years. To understand why this matters so much, we first need to understand why lithium became king. Before the early 1990s, batteries were, let's just say they weren't winning any awards. Camcorders barely lasted an hour. Laptops were bulky enough to double as arm workouts. And carrying a phone that lasted all day sounded more like science fiction than reality. Then, lithium-ion batteries arrived, and everything changed. They stored nearly 3 times more energy than older battery technologies while taking up far less space. That single breakthrough made smartphones possible, gave us ultra-thin laptops, wireless earbuds, power tools, and eventually electric vehicles. Modern portable technology exists because lithium changed the rules of energy storage. Naturally, the world went all in. Governments invested billions. Companies built enormous factories. Researchers spent decades making lithium batteries even better. Once a technology works that well, nobody wants to gamble on something different. But history has a funny habit. The moment everyone believes they've found the perfect solution, that's usually when its biggest weaknesses begin to appear. And those hidden weaknesses would eventually send scientists searching for an alternative that had been overlooked all along. For nearly 30 years, lithium-ion batteries seemed unbeatable. Every new smartphone lasted longer. Electric vehicles became practical. Power tools got lighter and more powerful. Year after year, engineers kept improving lithium, and the world simply assumed it was the future. But underneath all that success, a few serious problems were quietly growing. One of the biggest warning signs came in 2016 with Samsung's Galaxy Note 7. At first, everything looked perfect. The phone received great reviews, pre-orders were strong, and customers couldn't wait to get one. Then reports started coming in. Phones were catching fire, some ignited in people's pockets, others overheated on nightstands while charging. Airlines even banned the device from flights, and Samsung eventually recalled the entire product line, costing the company around $5 billion. Now, Samsung made mistakes in the battery's design. But here's what many people missed. The real danger wasn't unique to that phone. Every lithium-ion battery contains a liquid electrolyte that helps move energy between the battery's electrodes. The problem is that this liquid is flammable. If the battery overheats, gets damaged, or is charged under the wrong conditions, the electrolyte can ignite. And when one battery cell catches fire, it can quickly heat the cells beside it. Those cells ignite too, creating a chain reaction engineers call thermal runaway. Once it starts, stopping it becomes incredibly difficult. Safety wasn't the only concern. Cold weather became another major challenge. When temperatures drop below freezing, lithium ions move much more slowly inside the battery. Over time, tiny metallic spikes can begin forming during charging. If those spikes grow large enough, they can create an internal short circuit. Even when that doesn't happen, cold temperatures still reduce performance dramatically. Around the freezing point, lithium batteries can lose 20 to 40% of their driving range. For someone driving an EV in northern states, Canada, or other cold regions, that could mean losing over 100 kilometers of range simply because winter showed up. Then another problem hit, and this one had nothing to do with engineering. Between 2020 and 2022, the price of lithium's key raw material increased by 8 times. Then, just a year later, prices crashed by more than 70%. Manufacturers suddenly realized they were building the future of clean energy on a material with wildly unpredictable costs. That was the turning point. Car companies wanted lower costs. Governments wanted a more secure supply chain, and researchers started asking a question they hadn't seriously considered in years. Was there another battery chemistry waiting in the background? As it turns out, there was, and it had been sitting quietly in scientific research for decades. So, if lithium had all these problems, why didn't the industry just switch to something else? The truth is, they almost did. Long before lithium became the face of modern batteries, scientists were already studying sodium. Since it sits directly below lithium on the periodic table, it behaves in many similar ways. The biggest difference? Sodium is everywhere. It's found in seawater, underground minerals, and even in ordinary table salt. Unlike lithium, which is concentrated in a limited number of regions, sodium is one of the most abundant elements on Earth. Back in 1966, Ford Motor Company built one of the first rechargeable batteries powered by sodium. It proved the concept worked, but there was one huge catch. The battery only operated at around 300 degrees Celsius. That's incredibly hot. Great for a laboratory demonstration. Not so great for something sitting underneath your family car. Then everything changed in 1972. Researcher Stanley Whittingham successfully developed a lithium battery that worked at room temperature. That breakthrough completely shifted the industry's attention. When Sony released the first commercial lithium-ion battery in 1991, manufacturers, investors, and researchers all jumped on board. Over the following decades, more than $1 trillion flowed into improving lithium technology. Sodium wasn't abandoned because it failed. It was abandoned because lithium was already winning. Still, sodium had one major problem that nobody could solve. Sodium ions are about 35% larger than lithium ions. Inside a battery, those ions constantly move in and out of a carbon material called graphite. Lithium fits perfectly into graphite's tightly packed layers. Sodium doesn't. Every time sodium tried to squeeze into that structure, it damaged the material. After only a few hundred charging cycles, the battery's performance dropped dramatically. That single challenge kept sodium batteries out of commercial use for more than 40 years. Then, around the year 2000, researchers made a discovery that changed everything. Instead of using graphite, they developed a different material called hard carbon. Unlike graphite's neat, organized layers, hard carbon has an irregular structure filled with tiny pockets. Those extra spaces turned out to be exactly what sodium ions needed. They could move in and out without damaging the material, finally solving the problem that had frustrated scientists for decades. It was a huge breakthrough. But discovering something in a lab is one thing. Turning it into millions of reliable batteries that people can actually buy is a completely different challenge. And that's where one company decided to bet billions of dollars on an idea the rest of the industry was still ignoring. Finding hard carbon was only half the battle. The real challenge was turning that scientific discovery into a battery that could be manufactured by the millions. That's where CATL, the world's largest battery maker, stepped in. While many companies stayed focused on lithium, CATL spent nearly 10 years and invested around $1.5 billion developing sodium-ion technology for large-scale production. The first obstacle was moisture. Hard carbon naturally absorbs water, and even tiny amounts of moisture inside a battery can react with the electrolyte, creating gases that slowly damage the cell. Building one battery in a laboratory is manageable. Building millions with consistent quality is a completely different challenge. CATL solved this by changing the surface of the hard carbon, making it repel moisture instead of attracting it. The company also developed a way to precisely control the tiny pores inside the material. If those pores were too small, sodium ions couldn't enter efficiently. If they were too large, valuable storage space would be wasted. Years of engineering finally produced the perfect balance. The result was a commercial sodium-ion battery called Naxtra. Its performance surprised the entire industry. According to CATL, a vehicle using Naxtra can travel over 500 kilometers on a single charge, while charging from 10% to 80% in just 15 minutes. Even more impressive, the battery is designed to last for more than 10,000 charge cycles, giving it a lifespan of roughly 27 years if charged once every day. Cold weather is where sodium-ion batteries really shine. While lithium batteries lose a significant amount of range in freezing temperatures, Naxtra continues operating at temperatures as low as -58 degrees Celsius. Even at minus 40 degrees Celsius, it still retains about 90% of its capacity. For drivers living in cold climates, that could make winter driving far more reliable. There's another major advantage: cost. CATL says its sodium-ion cells can be produced for around $19 per kilowatt-hour, compared to roughly $55 to $70 per kilowatt-hour for comparable lithium-ion cells. On top of that, sodium is abundant around the world, reducing the supply chain risks and price swings that have affected lithium in recent years. Does that mean lithium is finished? Not at all. Lithium still stores more energy in a smaller, lighter package, making it the better choice for smartphones, laptops, and other compact electronics. Instead of replacing lithium completely, CATL believes both technologies will work together. The company has already developed battery packs that combine lithium-ion and sodium-ion cells, allowing each chemistry to perform the jobs it's best suited for. That brings us back to the record-breaking 60 gigawatt-hour sodium-ion battery order we mentioned at the beginning. A technology that sat quietly in research papers for more than 2 decades is finally entering the real world. Sometimes the next big innovation isn't about discovering something new. It's about giving an overlooked idea the chance it always deserved. So here's the question. If a sodium-powered electric car cost less, lasted longer, and handled winter better than today's EVs, would you choose it over a lithium-powered one? Let us know in the comments below.